All right, here we go again. This is section 4-3. This is the multiplication rules and conditional probability. All right, so as always, I'm trying to clarify, help you understand the text. I would say right here is a little bit of a confusion. It's very easy to be confused. All right, so 4-2, we talk about the addition rules to compute the probabilities for events that are either disjoint or not disjoint. So if they're mutually exclusive, we say that the sets are disjoint. If they're non-mutually exclusive, they're not disjoint. Now we're going to talk about the multiplication rules. Well, the multiplication rules can be used to find the probability of two or more events that occur in sequence. Well, what the heck's the difference? Why do we have a different rule? It sounds exactly the same. It's the probability of two or more events that occur in sequence. Okay, so it sounds very similar. Now it's hard because you don't, it's too hard for me to go bouncing back and forth, but I'll just read it from the book. And hopefully you have your book and you're looking as well. If you look back on page 201, section 4.2, talking about the addition rules for probability, it says, many problems involve finding the probability of two or more events. So what's the difference? In section 4.2, we're just talking about the probability of two or more events, like being a female and being a Republican. Here in section 4-3, we're talking about two or more events that occur in sequence. So that's the distinction. They occur in sequence, one after another. So you toss a coin, then you roll a die. So you're doing two different things, one after another. Now the reality is, of course, you can do them at the exact same time, but the concept is you're doing them one after another. Okay? So you can find the probability, if you do that, of getting a head on the coin and a 4 on the die. We say that they're independent. So now we're not talking about the disjointness so much. Now we're talking about finding the two events, and we want to know, are they independent or not? So what we'll see is that there's different rules depending upon whether they are independent events. And the concept is that they are independent since the outcome of the first event, that's tossing the coin, does not have any effect whatsoever on the outcome of the second event, specifically rolling a die. Now that's just common sense, right? If I toss a coin and then I throw a die, how could it possibly have any influence? So we say that the two events A and B are independent if the fact that A occurs does not affect the probability of B occurring. Okay. Now let's be very clear on the language here. The events A and B. The event is not the flipping the coin. The event is not tossing the dice, tossing the die. The event A in this example might be up here where they say flipping the coin and getting a head. So the event A up here is getting a head. The event B is getting a 4 on the die. So make sure you pay attention to that language. The language is very important, okay? So here's some other examples. You're rolling a die, you get a 6, then you roll a second die and you get a 3. The dies aren't connected. They aren't talking to each other. So that's why they're independent. Same idea with drawing cards. Okay. So what do? How do we do this? We merely multiply. So here we go. If they are independent, the probability of both occurring, so A and B. So A is, as an example, flipping a coin, and getting, let's see, getting a head. So probability of a head and a 4 is the probability of the head times the probability of the 4. So it's H stands for head, T stands for tail, and for the die, the possible outcomes are 1, 2, 3, 4, and 5, and 6. Okay, so the probability of getting a head is 1/2. The probability of getting a 4 when you toss the die is 1 out of 6. So that's why we're multiplying them together. And the concept is very simple. If you think about it in terms of, is there any memory? Does the second event have any memory of what happened in the first event? That's how I look at it. So like when you toss dice, if you get a 5 and a 5 and a 5 and a 5, what's the chance of getting a 5 the next time, it's still the same as it was before. That die does not remember what it did before, so they are independent events. Okay, so I'll let you take a look at this. Drawing the card is the same basic idea. You know, it's always going to be the same thing. Is there any sort of memory going on here? Now, the only nuance here is we'll see later on how important it is to talk about whether you have replacement or not, and we'll see that later on. But here, the card is drawn from the deck and replaced. So you're taking a card and then you're putting it back into the deck. Then you draw the second card. So the probability of getting a king and then a 7, well, there's 4 kings, so there's 4 successes, 4 ways of getting a king, and then on the denominator, the number of possibilities in the sample space. This is like what we talked about before. On top you have the number of successes, and on the bottom you have the number of events in the, or occurrences, I guess I should say, the number of occurrences in the sample space. So there's 4 ways of getting a king, and there's 52 possible cards. Since you put the card back, you still have 52 in the denominator here. If you didn't put it back, well, then that would change things, right? I mean, you know, now all of a sudden the top is going to be different, the bottom's going to be different. If you pull a king out, now how many kings are left in the deck if you don't put it back? Well, there's only 3 on top, but and in the bottom there's not 52 cards anymore. Now there's only 51. So it's very important to know, are you or are you not replacing the card? Okay, so I'll let you do the arithmetic. Okay, so we get the colored balls. You know, we use the colored balls just as an example, as a metaphor for other more interesting problems. It just helps us understand the problems, okay? So here again, we have 2 red, 5 blue, and so forth. The ball is selected, the color is noted, then it is replaced. So those are critical issues here, a critical point, that it is replaced, okay? Then you select the second ball, and its color is noted. Okay, so now what's the chances of getting 3 blue balls? Okay, well, since you're replacing, the denominator never changes. So there's how many balls are there altogether? There's 10, right? 2 plus 5 plus 3. There's 10 balls altogether. So the denominator is clearly going to be 10. To get a blue ball, there's 5 blue balls according to what we're given. So, you know, it's 5 over 10 times 5 over 10 times 5 over 10. To get a white and a red, okay? So there's 3 ways of getting the white, and then there's 2 ways of getting the red. That comes from right up here. There's 3 whites and there's 2 reds. Okay, so all of these kind of basically follow the same pattern. So as he says here, the multiplication rule, number 1, can be extended to 3 or more independent events. You just keep on going here. It doesn't matter how many events there are. Now, this letter K here, that's just to tell you that's my last number, or I'm sorry, that's my last independent event. So event A, event B, event C, keep on going all the way up to K. So however many you want, okay? Okay, so now here's a point. When a small sample is selected from a large population and the subjects are not replaced, the probability of the event occurring changes so slightly that by and large we're going to figure that it stays the same. Okay, so up above we did the replacement. In a minute here we're going to take we're going to do a example where we don't do the replacement. Okay. Okay, I'm not too crazy about this bank robbery example. I'll let you read that. Here's a medical one, male color blindness. Okay, 9% of men have this certain type of color blindness. Okay, so it's 9%. So you pick 3 men at random. Find the probability that all of them will have this type of red-green blindness. Okay, so the concept here, what the point of this example is that you're picking these 3 men, but you're not putting them back into the sample, right? I mean, or into the population. You know, before we were picking a ball and we put the ball back into the bucket. Now we're picking these 3 men, but you're not putting them back into the population. You're not, you know, you wouldn't want to pick the same man again, right? So you're picking the 3 men out of the millions of men that are in the United States. So even though you're not replacing, it changes things so slightly that we just tend to ignore it. That's the point of this exercise. So if you got three guys, three men, you pick them at random, probability of, we consider them to be independent, because if you pick man number one, he does not affect man number two. If man number one is colorblind, that has nothing to do with man number two being colorblind, and that has nothing to do with man number three being colorblind. So that's why they're independent. So we can just multiply them. So it's 9%. So it's 0.09 times 0.09 times 0.09. So boom, there it is. There's the there's the answer. So you round that off to 0.0007. So there's a 0.07% chance that all three men selected will have this exact color blindness. Okay, so in these examples we just looked at, all of these examples, 4-23, 4-27, the events are independent because the occurrence of the first event or the second event or the third event, whatever, it in no way affects the outcome of the second event or the third event or the fourth event. So that makes sense, right? However, we will have situations where the occurrence of the first event does change the probability of the occurrence of the second event. So this is where we have to kind of be cautious and say, well, these things are happening one after another in some way. So we now say that the two events are dependent. So let's say we take a card from the deck and we do not replace it, and then we select the second card. What's the probability of selecting an ace on the first and a king on the second? Well, things are going to change because you did not replace the card. Okay, so they are dependent. On the first draw, you pull an ace out. There's 4 ways out of 52. So you pull the first ace. You pull the ace out. If you do not replace that card, the probability of selecting a king on the second card, well, there's still on the top. That's the number of successes. There's still 4 possible successes. There's still 4 kings, but there's only 51 cards in the denominator. So there's only 51 outcomes possible in the sample space. So there's only 51 cards because you did not replace that card. You see what's going on here? It's just a matter of, hey, I didn't replace it, so the denominator is going to change. Okay. All right. So when the outcome or the occurrence of the first event does affect the outcome or occurrence of the second event, in such a way that the probability has changed, the events are said to be dependent events. So you draw a card from a deck, you don't replace it, boom, that makes it dependent. You draw a ball from the urn, you don't replace it, that affects things. How about being a lifeguard and getting a suntan? Well, of course, if you're a lifeguard, you're going to be out in the sun most of the time, right? Maybe you're at an indoor pool, but you know, a typical lifeguard. So if you're a lifeguard, that's going to affect your probability of getting a suntan. Having high grades and getting a scholarship, that's just the way it works. You get high grades, chances are better that you're going to get a scholarship. Okay, so you can kind of see how this works, right? So you use the multiplication, but you have the multiplication rule, but you do have a modification in the notation. Okay, so it changes things. So what we usually say is we say, well, the event of getting a king on the second draw, given that an ace was drawn the first time, we call that a conditional probability. So we use the word given. So we have a first event and then we have a second event. So we say, well, the probability of the second event occurring given the first event occurs. It affects things, okay? All right. So that's called a conditional probability. So here's the notation. The notation for conditional probability is the probability of B given A has occurred. Be cautious. This little vertical line does not mean division. It's what I just said. It's that it is given that a certain event has already occurred. Okay, so I'll let you read that. It's pretty clear, I think. So now we have a new multiplication rule. That'll be in the next video. So let me end this video.